Hello viewers on YouTube. In this video tutorial, we are going to consider scalar and vector. We are going to go over the physics problems we might encounter involving vectors and scalar. So what exactly is a scalar? Scalar are quantities that has magnitude and unit only. And an example of that is speed and distance. Now for the vectors, they are magnitude, unit and direction. And an example of that is velocity and displacement and so on. Now, when it comes to arithmetic, that is problems involving scalar and vector, to add scalars or subtract scalars, it's very straightforward as the usual arithmetic can be done on it. But when it comes to vector, we don't just add or subtract them, but instead we pay attention to the direction. Take for instance, the sum of two speeds that are moving, if the first one is moving to the left, for instance, we have 5 meters per second, and the second speed, that's 6 meters per second. Now to add these two speeds, we really don't care where this is heading to, we just have it as 11 meters per second, as that is the addition or that's the sum of the speeds. Or if this is velocity, if they are velocity, the direction plays a very crucial role. As this 5 won't be just 5, but instead -5. So the sum of these two velocity, if they are meant to be velocity, will simply be -5 plus 6, which will be +1. So that results in +1 meter per second. So if that is velocity, so just note the difference. When you are adding two scalars, don't pay attention to the sign. But when you're adding vectors, the sign is very, very important. Now, you can still ignore the sign if those vectors are heading towards the same direction. Take for instance now, assuming we have the velocity of an object from point A to a certain point B to be 5 meters per second as well. Now, the velocity of this same object from A to point C is 3 meters per second. So the fact that these two velocities are towards the same direction, then finding the sum by just adding 5 and 3 makes sense. It makes good sense, okay? That's just 8 meters per second. This doesn't alter your result, as this is very, very perfect and it's a good job. However, when they are being headed towards different direction, be careful about the sign while adding them, okay? Now, instead of two vectors being parallel to themselves, either towards the same direction or towards different direction, what if we have two vectors to be perpendicular to themselves? How can we find the sum of these two vectors? Okay, to find them, you can't just add them just like that, but instead use a theorem which perhaps you might have been familiar with. So, if the first vector is directed towards the vertical axis, it's a downward, and the other one is towards the horizontal axis, that's the rightward. Okay, if this is the first one facing downward and this is the second one, okay, perfect. Now the resultant vector, according to the theorem we'll be using, which is simply the Pythagorean theorem, is simply the magnitude of the hypotenuse side of the triangle, connecting the starting point of this one to the end point of this one. Okay, perfect. Now I will instead denote this hypotenuse with R, as that's the most often used. Now if this vector y or of magnitude y, and this other one is a vector of magnitude x, then the resultant, the square of the resultant according to the Pythagorean theorem, is simply equals to the sum of the square of the other two vectors. And finally, we can get the value of r to be equals to the root of y squared plus x squared, and that's it. Now sometimes you won't just be required to find the magnitude of the resultant vector, but also its direction. Now the direction for two vectors that are perpendicular to themselves would be the value of angle theta. as that will be the angle at which the resultant vector subtended with the horizontal vector or the horizontal ground. Now to find theta, notice that some of the trigonometric function, most especially the tan function, can help us. As regardless of how the problem comes, the magnitude of the first one and this other vector will be given. So therefore, that corresponds to tan theta, okay, equals y over x. So the value of theta would be equals to the tan inverse or the arctan of y over x. So whatever answer you have for this tells you the direction of the resultant vector. Now to understand this more better, let's consider an example. Example number 1. A man starts from point A and walks 3 kilometers eastward and then 4 kilometers southward. Find the resultant of the man in magnitude and direction. So we need the magnitude of that man and its direction. So let's interpret this problem. So according to this problem, a man starts from point A. So let's assume this is point A. Now he walks 3 kilometers eastward. Now don't forget your cardinal points. The north is all the way upward, south is downward, west is left, and east is towards the right. So therefore, the man walks in this direction. So 3 kilometers eastward. So that's displacement, okay? Perfect. Now, the now said after that, he then walked 4 kilometers southward. So he then head all the way downward, 4 kilometers southward. 4 kilometers southward. So the goal is to find the magnitude of the resultant vector of this man. So this is the starting point, and this is the end point. So we need the value of this line. Perfect. So let that line be r. Now according to the theorem, we said r squared is equal to 3 squared plus 4 squared. And proceeding forward, 3 squared, which is 9, plus 4 squared is 16. And eventually, r is equal to the root. So the sum of 9 and 16 is 25. That gives us 5. So therefore, the resultant of the man in magnitude is 5 kilometers in displacement. Perfect. Now what about the direction? We said the direction of the man would be the angle subtended by the man to the horizontal. Now be careful. This is not where theta refers to. At this position, it's not the angle between the resultant vector and this is the horizontal. This is vertical, okay? So this is the horizontal. Another way you can think about it is to probably draw an horizontal line here. Okay, now this angle tells us the angle between the horizontal vector and or the horizontal ground and the horizontal vector. However, this angle, according to our knowledge in geometry, will be alternate to this angle. So that position is the best one to select. So this is where theta refers to. So if theta falls there, what functions connect that? Okay, well, notice that it's still tan function, but this time around the opposite will be 4, as 4 is one facing the theta. So therefore, tan theta would be equals to the opposite y, which is 4, divided by the adjacent 3. Now, if I should head right onto my calculator and type 4 divided by 3, I got 1.33. So eventually, tan theta is equal to 1.333. Repeating, just have like that. So taking the arctan of both sides, theta is simply tan inverse of 1.33 repeating. So eventually, when I take the arctan of 1.33, so I end up having 53.06 degree. So this is the direction of the resultant vector, and this is the magnitude. So that's how to easily find the magnitude and the direction of the resultant vector of two vectors that are perpendicular to themselves. Now that you know how to find the resultant vector of two vectors that are perpendicular to themselves, let's talk about something called resolution of vector. So what exactly is a revolution vector? Now let's take, for instance, instead of having two vectors to be perpendicular to themselves, okay, and then being required to find the resultant vector, what if we have the resultant vector and then being required to find the other two vectors that will have the same effect as this resultant vector? As you can see, that question seems like the reverse process. Now the question is that possible? Can we find two vectors that will have the same effect as a single vector? As long as that single vector serves as the resultant vector of those two vectors, then definitely it's possible. Now the process of doing that is called the resolution of vector. So now how do we resolve vectors? That's what we want to consider focusing on now. So let's say we have a particular vector or resultant vector to be this. So if this is heading towards this direction, for instance, and let's say its magnitude is f. Assume it's a force, for instance, right? Good. Now to resolve this vector, since there's a force, let's draw a vertical part of it. Let's draw it upward like this. Okay. Now let's draw an horizontal part of it like this. Now you notice that this angle will correspond to the direction of the resultant vector, as it is the angle between that vector and the horizontal. Okay, perfect. Now if I should draw a line joining this point this way, as you can see, these and these are parallel, so they might be of the same magnitude. In fact, at this point, perfect. Now let it be y, let it be x. Now notice that we can definitely find y and x using some of the functions. According to the sine function, the sine of theta is opposite, which is y over hypotenuse over f. Okay, so that's y over f. And if I solve for y is simply equals to f sine theta. So that will be equation 1. Now for x part, let's use the cosine function. The cosine of theta is x over f, adjacent over hypotenuse. And if I isolate x, I have x to be equals to f cosine of theta, equation 2. And this is what we need. To resolve a certain resultant vector into its components, to find its y component, just multiply the vector by the sine of the angle given to you. Alright? And make sure that angle is the direction of that resultant vector. And to find the resultant component, you multiply it by the cosine of that angle. Now sometimes, instead of having it as y, or in some textbooks you might see it as f sub y, and see this one as f sub x. So don't panic, they are referring to the corresponding component respectively. So how does it work? Let's consider an example. Resolve a force of 100 Newton inclined at 50 degrees to the horizontal into the horizontal and vertical components. So we are given that the resultant vector is 100 Newton and they said it's inclined at 50 degrees. So now, let's assume this is the resultant vector. So it's of magnitude 100 Newton. Now, this will be its vertical component and this will be its horizontal component. So let the vertical component be f sub y and let the horizontal be f sub x. According to the problem, this 100 Newton resultant vector or resultant force is inclined at 50 degrees to the horizontal. So therefore, this position is 50 degrees. Perfect. Now earlier we said f sub y is simply f sine theta. Whatever in this case is 100. So that will be 100 sine 50. Also, we said f sub x is f cosine theta, and therefore we have 100 cosine 50. So let's type that into our calculator. So when I type 100 side 50, I got 76.604. Okay, it's a force to be in Newton. And for the other one, 100 cosine 60. 100 cosine 50, not 60. So I got 64.28 approximately. So that is the component for the resultant vector, both the horizontal and the vertical part. So that's how to easily resolve a vector. So kindly keep that in mind as we might be referencing to that as we proceed forward. Now, sometimes the two vectors given to us might not be parallel or perpendicular to themselves, but instead they will be at an angle to themselves. They will be subtending an angle with each other. Now, in this case, how can we find the resultant vector? Alright, so that is the third case in which problem can come on vector. The first case we have talked about parallel, so you can do the normal algebraic addition if they are heading towards the same direction. Otherwise, pay attention to the signs. The second case is perpendicular. We use the Pythagorean theorem. Now the third case, when they are at an angle to themselves. Now, to find the resultant vector for two vectors that are at an angle to themselves, for instance, let's assume this is the first vector. Let it be vector A, and let it be the second one, vector B. Alright, to find the resultant magnitude, we are going to consider using a law called the parallelogram law of vector. And it says that when two vectors are represented in magnitude and direction by the adjacent side of a parallelogram, as you can see, they seems to be represented by the adjacent side of a parallelogram, because we can definitely complete this and have it as a parallelogram. Alright, that makes sense. Now, when two vectors are represented in magnitude and direction by the adjacent side of the parallelogram, this is the magnitude, this is the magnitude, this is direction, this is direction. Okay, perfect. Then the diagonal of the parallelogram, okay, represent the resultant vector of the two vectors in magnitude and direction. It is the diagonal of this parallelogram. Let me use the dotted line for that. Will represent the resultant vector of these two vectors in magnitude and direction. Now, the question you might want to ask is, how do we now find the resultant vector? Okay, to find that, we can use the cosine rule. So according to cosine rule, let's complete the parallelogram first. We will complete the parallelogram now. Okay, so the goal is to find this. To find R now, since we know that some of the properties of parallelogram is that opposite sides are the same, this will still be B and this will still be A. Okay, now the vectors has been combined in such a way that we now have starting point. This can be the starting point, and this is the end point. That makes sense. It's no more tail to tail or head to head. Now it's from tail to head. Perfect. Now, to find R within this angle, but we also know that for properties of parallelogram, the adjacent angle are supplementary. They are supplementary. That is, if you are given the angle between the two vectors, there's no way they will give you. Let that angle be theta, but we need alpha, which is the other angle. Know that theta plus alpha is equal to 180. If you are wondering why they are equal to 180, because they are supplementary. You can say the adjacent angle of a parallelogram. Yes, the adjacent angle of a parallelogram. That's the reason. The opposite angle, the opposite angle of a parallelogram are the same, while the adjacent angle are supplementary. So therefore, the reason will be adjacent angle, okay, of parallelogram. Okay, you can just put parallelogram and you have it to be like that. So now, if we solve for alpha now, alpha will be equals to 180 minus theta. So once you have that, that's it. Now, From the cosine rule, to get the value of r, we know that the square of the side you are looking for is equal to the sum of the square of the other two sides. Okay, that's b squared plus a squared. Okay, then minus 2 times the other two sides again, 2ab multiplied by the cosine of the angle facing the side you're looking for. That's cosine alpha. Perfect. So that's what we'll be using to find the resultant vector for two vectors that are at an angle to themselves. Please be very careful. Make sure that if the angle given to you is acute, you will need to get the obtuse one. However, if the angle given to you is obtuse, you have to get the acute one. Yeah, if they are acting to themselves and the angle given to you is acute, except if you realize that the diagram is of this form already. Okay, that's when you don't need to do any subtraction. Are we together? We're going to consider an example. You're going to see what I'm saying in next sense. So now, what about the direction? How can we find the direction of the resultant force? You know, this is what we'll be looking for now. Let me use different color for that. This side, or this angle. Let me call that beta, because that's the angle between the resultant vector and the horizontal ground. How can we get beta? We already have this one entirely as 45. Well, that really don't even have any business to how we can get beta. So let's use sine. Let's use sine. Now, since this side will be given, okay, and once you find the resultant, we will have this side as well. From sine, we know that the resultant r over the sine of its angle, sine alpha, will be equals to the side facing what we are looking for. That's a over sine of beta, sine beta. Perfect. And after that, we just need to find beta and get the direction of the resultant vector. I hope you understand and get what I'm saying makes sense. So that's how to find the resultant vector and the direction of the resultant vector for two vectors that are at an angle to themselves. Perfect. So now let's consider an example. Find the magnitude and direction of the resultant vector of two vectors, 3 units and 4 units, acting at a point O at an angle of 45 degrees with each other. So we are told that the vectors 3 units and 4 units are acting at point O. So for two vectors to be acting at a point, then their tail will be touching themselves, or their heads will be touching themselves. So let's use the tail this time around. So this is the first one. Okay, it will be head. This is the head. This is the tail. So we will have the tail of the second one right here. The angle between them is 45. Okay, I think the way we are moving it is okay. So this is the second one. So the angle between them is 45 degrees. 45 degrees. Perfect. Okay, now let this one be of 4 units and let this one be of 3 units. Okay, the goal is to find the resultant vector, and now we said the resultant vector will be the diagonal of the parallelogram. So if we join this parallelogram now, okay, the goal is to find r. Now we said this side will also be 4. R squared will be equals to 4 squared plus 3 squared, then minus 2 times 4 times 3 cosine of, now we need this angle, that will be 180 minus 45. So 180 minus 45 gives us 135. So this one is 135 cos 135. Perfect. So r squared is equal to 4 squared is 16, 3 squared is 9, minus 2 times 4 times 3, that's 24 cosine 135. So we have r squared equals 16 plus 9 is 25, minus, so let me type in 24 cosine of 135. Okay, so I got what's it called for that? I got negative 16.97. So multiply by negative 16.97. So be very careful. You do it one after the other. X squared equals 25. So the minus affect plus 16.97. Alright, and when we had 25 with 16 plus 97, we got 41.97. Finally, you just find the root of 41.97, and boom, we are good to go. So that gives us 6.48. Okay, it's a vector, so we put units. So that is the resultant vector of the two vectors. Now that we have the resultant vector, let's find the direction of the resultant vector. Okay, let's find the direction. Now we have gotten the value of r to be 6.4. Now we know that according to sine rule, 6.48 divided by the sine of the angle, sine 135. Okay, that sine of the angle facing it will be equals to 4, okay, sine whatever we are to use to represent it. Okay, let it be beta. Let it be beta. So that's 4 over sine beta. If I cross multiply, we have 6.48 multiplied by sine beta equals 4 sine 135. Alright, sine beta is equal to 4 sine 135 divided by 6.48. So I've actually divided both sides by 6.48. So let me type that into my calculator. So I'm typing straightforward. 4 sine 135. Okay, I close the bracket. Divided by 6.48. So I got 0.436. So we have sine beta equals 0.436. And taking the arc sine of both sides of sine inverse, we have the sine inverse of 0.436. And I take the sine inverse of 0.436, I got 25.8. So that is the direction, I said 85 degree of the resultant vector. So that's how to find the magnitude and direction of resultant vectors of two vectors that are at an angle to themselves. So now the last thing we have to consider in problems involving vectors is how to find the resultant vector of coplanar vectors, which is also called system of vectors. So how do we do that? Let's look into that as well. So consider this example. I would like to disclose the concept using an example, as I believe that would be the best way. So we have to calculate the resultant vector of the 5 coplanar forces, and we have to find its direction as well. Though the problem doesn't ask us to find direction, but I'm going to show you how to find the direction of the resultant vector of system of forces. Perfect. So here's what you need to know. What we are going to do is that we need to resolve all these vectors into their components. So after resolving them into the components, we now add all the y components of each of them together and all the x components of each of them together. Now, the x component and the y components of the what we added will be perpendicular to themselves. We will now use these values. We use Pythagoras theorem. We use on them to get the final resultant vector. Okay, so whatever answer we have like that will be our final resultant vector, and we still use them to find the direction of that vector. So what are we saying? When you have something like this, you will solve the first one. Make sure that the angle you'll be using should be the angle between that vector and the resultant. If you are given this kind of angle here now, don't use it like that. Instead, you subtract it away from 90 and get this other one. I will get my point. Make sure it is the angle between the horizontal and that vector. Now, we're solving the 20 Newton force to its component. We know that, let me just say Fy20, that will be equals to the value of its magnitude, 20 sine the theta 40. Now, Fx20, that will be 20 cosine 40. We have talked about the formula earlier. Okay, this tells us the horizontal component of that force, and this tells us the y component of the force. Y finding the y component, you use sine. Y finding the x, you use cos. Okay, now let me type this in my calculator straightforward. So 20 sine 40, I got 12.85. 12.8, let me just say 86 approximately to 2 decimal place. Also 20 cosine 40, I got 15.32. Perfect. Now on to the second one, right? Now this is a force as well. It's also a force, and it has the magnitude. This is 15, 16, 20, 12. So that will be for the 10 Newton. Alright, so I actually omitted it for the 10 Newton force. I should make it an exercise. Let's continue. Now, let's do for 12 Newton now. Fy12 gives us 12 sine. The angle between the horizontal and that force is 50, sine 50, and Fx12 is 12 cos 50. So what would that be? So 12 sine 50, that gives us 9.19, and 12 cos 50, 12 cos 50 gives us 7.713. Let me leave this to this map, please. 7.71. Now onto this one, the one I just introduced. That's for 10 Newton. So Fy10 now will be equals to, the magnitude is 10. That's 10 sine. Now the angle, as you can see, is already on the horizontal, so the angle is 0. It's parallel to the horizontal, so that's 0 sine 0, and Fx10 now will be 10 cos 0. Alright, 10 sine 0 gives us 0. Okay, now what about 10 cos 0 gives us 10? Cos 0 is already 1, that gives us 10 back. Perfect. Now on to this one. Now the angle it's obtained with the horizontal is 60, as you can see. This is the horizontal and this is the force, so that's 60. That makes sense. Okay, perfect. So we have, let me detail this. Okay, 15. So Fy15 equals, so the magnitude of the force is 15 Newton. That's 15 sine 60, and Fy or Fx15 equals 15 cos 60. Right, so 15 sine 60 gives us 12.99, and 15 cos 50 or 60. I don't know what's wrong with my calculator. It's just typing something else. 7.5. Perfect. Now on to the last one. So for the 16 Newton, Fy, let me use yellow color so that you won't mix them up. Fy16 equals, so that's 16 sine 60, and for the other one, Fx16 equals 16. Why are you 60? Oops. The angle between the horizontal and this one is not 60. As you can see, this is the horizontal and this is the vector, so that will be 90. So this is the angle, that will be 90. Perfect. So 16 sine 90, 16 cos 90. Oops, what's wrong, man? 16 cos 90. Okay, perfect. Now 16 sine 90, 16 sine 90 I got 16, and 16 cos 90 will be 0, plus cos 90 is already 0. Perfect. Now, this will be your final answer. After you have resolved everything, each of those forces, that's not everything you're going to do. Okay, that's not all. The next thing you now do now is to go back to those vectors. You will now want to pay attention to the direction. Though some of you, after disclosing what I'm about to say now, if you want, you might just do it right from start. But I don't want you to now make mistake. That's why I used to suggest that you will solve it first, then after that you now go and be paying attention to the signs you'll be attaching to them. Okay. Now, as you can see, let's start with this one. As this vector, where it is heading is that it's going towards the positive y-axis upward. However, it's going towards the negative x-axis. Now you now go to the y component of it. As you can see that since it is going to the positive y component, multiply this answer by positive sign. This answer times positive sign does not change anything. Perfect. But it is going towards the negative x-axis. So definitely its x component we have to multiply it with negative sign. So 15.32 multiplied by a negative sign gives us minus. So minus has to be with this one. Are we together? Perfect. Now on to the second one, 12. As you can see, as it is going up, positive y-axis, and as going right, positive x-axis. So its values has to be positive. That makes sense. Perfect. Now for this one, it's not going up, only going towards the positive x-axis. So that's why it does not have y components. That's why the y component is 0. So you multiply it with positive, does not change anything, it will be perfect. Now for this one, as you can see, it's heading towards the positive x-axis, but it's going downward the negative y-axis. So we have to multiply its y component with minus, while we multiply its s component with plus. Please, I hope you are following me. These are vectors, not scalar. The direction matters. That's why we're doing this one. Just go to that vector, notice where it is directed to for each of those components. Then you take the sign that is expected to be and multiply with its value. Simple as that. Are we together? Perfect. Now, the y component of 15, we are multiplying with minus. Okay, so minus will be here as well. And finally, for the 16, the y component will also be multiplied with minus. As you can see, it's going all the way minus. So this will be minus 16. And that's it. We are good to go now. Are we together? Perfect. Now the next thing is to add all the x components together and all the y components together. So you note down each of the answers, then we'll use these two answers on the Pythagorean theorem. Okay, to now find the entire horizontal vector. Whatever answer you have now is your horizontal vector. That's how to find the horizontal vector for system of forces of vectors. I don't need this anymore. I can get rid of it because I want to do the addition right now. Alright, okay. Now this side, capital delta x equals, so we think this one, that's negative 15.2, that means white color, minus 15.32 plus this one 7.71, okay, another one 10 plus 10 plus 10, okay, another one plus 7.5 plus 7.5, and this is 0, it's gone. So let's add it together. Okay, so I have negative 15.32 plus 7.71 plus 10 plus 7.5. Perfect. So I got 9.89. Good. So this is the total component along the horizontal path for the system of vectors or the system of forces, whatever vector it is. Good. Now for the y part we got 12.83 plus the other one 9.19 plus the third one, that's 0, it's gone. Now the fourth one is minus 12.99, the last one is minus 16 again, then minus 16. So let's add that together. 12.83 plus 9.19 minus 12.99 minus 16. So I got minus 6 points. That's minus 6.97. Perfect. So that is the total y component of the y component, which is the vertical component of the system of vectors. Okay. Now the entire resultant vector r will now be equals to the square root of x squared plus y squared. Okay. So that will be the square root of x is what? We got that to be 9.89. So we have 9.89 squared plus negative, well, since we are going to square it, I will not write it. The minus cancels out. It should get it off. We are squaring minus. So that will be 6.97 squared. But please, so you write it out for your teacher so that they can see that yes, you know what you are doing. So you write everything out so you can have your full marks. Perfect. Now, r becomes the square root. So let me square these values. 9.89 squared, 9.89 squared. I got 97.81, 97.81. Then plus, don't forget this point, plus 6.97 squared. No, I thought 94. 97 squared. 48.5. 48.58. Okay. So r equals, I'm adding it right now, 97.81 plus 48.58. 48.58. So I got the square root of 146.39. And finally, we got that. So the square root answer. So that gives us 12.009 or 099. 099. So since it is in Newton, we have forces. So that will be the resultant vector or the resultant force for the system of forces. Perfect. So guys, I hope you understand how to do this properly. Okay. First thing first, you resolve each of them to their corresponding components, to the y part and to the x part. After that, figure out the signs. Give the one with the right sign, give them their signs. Then after that, you add them together. Then you use Parallelogram rule to find the resultant vector. Now, once you have the resultant vector, to find the direction of the resultant vector for system of forces, use this the three functions. Now, we now use tan theta, the tan of the angle of that resultant vector, which is the direction of the vector, will be y over x, where y will be this one minus 6.97 and x will be this one 9.89. Are we together? Perfect. So I type that into my calculator. Negative 6.97 divided by 9.89. Alright, that's 0.704. So we have the tan theta to be equals to negative 0.704. Now the next thing is just take the arctan of both sides. Then we have 0.704. So let's add that into my calculator. So the tan inverse of 0.704. Alright. So I got negative 35 theta is negative 35.145 or 15 degree. So that is the direction of the resultant vector. So guys, that's how to easily find the magnitude and direction of the resultant vector of coplanar vectors or system of vectors. Okay, you have no bother about the negative part, as it tells us that the angle is measured in the clockwise direction. You understand? in the clockwise direction, not in the anti-clockwise direction. So that's why it is negative. So that's it. That's how it actually works. Okay. Feel free to share your solution to this problem via the comment section below, just for me to see if you have been following everything we have been discussing right from start. So I got 2 exercises for you that you are going to practice with. So here is the first one. So this is the third question I want you to do. Alright. Initially, my aim is to solve it as an example, but eventually I decided to make it an exercise. So that's the first one, and this is the second one. So let me get this first, then I show you the second one. So that's the second one. So for the first, we have to resolve it. While for this one, we have to find the resultant vector. Okay, for this one, you find the resultant vector for the system of vectors. While for the first one, let me confirm it again. Yes, you have to find the effective force. Yeah, you have to resolve it. You understand? So that's it. Thanks for watching. Feel free to subscribe if you want to. See you in the next video. Bye for now. Thank you.